What I want to look at here is circular motion, and this is our first steps into circular motion, and it's a little bit tricky. Try and draw a reasonable circle. What we have when we have an object going around in a circle, this is not a vertical circle, so let's pretend this is maybe something just traveling in a circle on a frictionless table or something like that. Or maybe something being swung with a little rope on it. The object at any time in its trip round there has a velocity like that. So that's its velocity. And if it was, say, an object that was joined by a rope, then this would be 90 degrees. So we would say that that velocity was tangential to the curve at a tangent. And the funny thing is, we're going to find that this is an acceleration. Remember, acceleration equals v divided by t, or delta v divided by delta t, right? But acceleration, we've thought of to a certain degree as delta s over delta t, or change in speed over change in time. And a change in speed is a change in velocity, because remember, velocity is a vector that has magnitude and direction. So if your speed changes, then that length of that arrow is changing, and therefore you have an acceleration. But what if just the direction changes, like it does in this thing? So as it comes around to here, it's going to be there. As it comes around to here, it's going to be there. So all the way around, this object's velocity is changing. And if the speed is constant, but the direction is changing, we still have an acceleration. And we give it a very special word. We call it a centripetal acceleration. And it's the acceleration you get when an object is going in a circle and it's changing its direction, but it's not changing its speed. Now, if we have two positions on the circle, maybe here and here, we have a velocity there. Our velocity just before was maybe like that. So we've got these two vectors. Now we know delta v is equal to v final minus v initial. And we know how to add and subtract vectors because we watched that little video. This is v final, this is v initial. So v final might look like that, right? But v initial, look, goes like that. So it actually has to go back this way. And so we've got these two vectors, and delta v ends up going like that. So the interesting thing is, when you draw this properly, and I urge you to do this, when you draw these vectors properly and do what I'm saying, you're going to find that the delta v points to the center of the circle. Interesting. So when an object goes in a circle, delta v points towards the center, but we said delta v over delta t equals acceleration. So that vector pointing towards the circle is an acceleration. So let's draw it again. So as an object travels all the way around here, it's always going to have an acceleration pointing towards the center. So when it's over here, its acceleration will point towards the center. And this is its centripetal acceleration. And looking back here, its velocity was tangential, but its acceleration was at right angles to that. So that's its velocity, that's its acceleration. I'll put a little c next to it, because it's a centripetal acceleration. If v was actually just changing length and going in a circle, then you'd have a combination of centripetal acceleration and tangential acceleration, right? And centripetal towards the center, we give that a name sometimes, we'll call it radial. So it's centripetal acceleration, it needs a force towards the center. So force equals ma. So if we've got an acceleration towards the center, we must have a force towards the center. We'll call it FC, centripetal force. So we have a velocity tangential, we have an acceleration towards the center, which means we have a force towards the center. Let's think about the other types of acceleration. If an object's just moving along with a velocity, if that vector keeps changing length, not direction, then we have delta S over delta T. It's a change in speed over change in time. Then we have an acceleration. That force, okay, is in the direction that the velocity is, not at 90 degrees. So it's not a centripetal force that would produce that acceleration. A centripetal force is at 90 degrees to the velocity. Changes the direction, not the magnitude of the velocity. So we give it that very special name. You can have a force at the same time changing the magnitude of that, and that would be called a tangential force. But nearly all the problems we do in level 2, we keep the speed constant and we just change the direction, and so all we're dealing with is a centripetal force and a centripetal acceleration. And when we do all the maths, I might do this in class, might not, we find that the actual numbers are like that. Centripetal acceleration is equal to velocity squared over radius. What velocity? This one. So if that's 20 meters per second, then that's the number we use for v. 20 squared is 400. If the radius is 10 meters, the radius is the distance from the center to the point where the object is going round, then that would be 10. 400 over 10, 40. 40 what? Meters per second, same units. All right? So if you want a centripetal force, how do you get it? Well, a centripetal force is just going to be the acceleration times the mass. I should do it around, you always use that. So if I want the force, I just multiply this formula by the mass, and I've now got centripetal force. So there you have the basics of circular motion and centripetal acceleration, centripetal force.